Now we were talking about the mass of an electron, and a lot of times when we refer to the mass of an electron, we call it the energy, or 0.511 electron volts. 0.511. The mass of a proton. I wish I could remember those numbers. But let's go back to the idea of the electron. Okay, we got an electron this big, and it has a volume, and it has a density. All right, well, does it matter what the shape is? I mean, nowadays they're talking about electrons are now made up of even smaller particles. Quarks, we're using quarks, and of course, if you've seen my email address, it is Quarkmaster. So I don't want to say I'm a master of quarks, but we do have quarks involved, and what we found out is that quarks also make up protons and neutrons, and quarks, and they come in 1/3 charges. You know, electrons come in negative charges, protons come in positive charges, but if you add up all the quarks, those are 1/3 charges. And then, of course, we got into tiny particles, baryons. So it doesn't matter how small we get. Let's choose the smallest particle we can imagine, and let's give it a shape, any shape. Now, let's say it's a ball. No matter what shape it has, if we give it a volume, we give it space. And once you give something space, then it has a density. And once it has a density, then you can get a mass. So we know even the tiniest particles that we've measured all have mass. So when we're talking about mass, we're talking about volume and space. But if you get any kind of volume at all, and you get, let's say we have any kind of particle, we'll actually get down to something that has true, absolute, total, contiguous density that occupies every single point inside its space. That's inside its volume. That is absolutely no empty space at all. No matter what that little piece is, if there's no empty space at all, a contiguous piece of matter with no empty space whatsoever, what you have is something with infinite density. Now, with infinite density, you don't have anything. It doesn't matter what the volume is. You have an infinite mass. Now, this is one of the great paradoxes of our very existence. We know that matter exists. We know that matter has mass, it has volume, it has density, but there can be no such thing as an object that is completely contiguous throughout its volume. There's no such thing. And this was epitomized, or this was brought forth by Zeno. I mean, Zeno's paradox, Zeno's arrow paradox, and many of his paradoxes defied the ideas and notions that we had about the nature of the universe. And I'm a Zeno fan. I think the man was right, even though Aristotle defied him, because he answered Zeno's paradoxes with, "This is not the nature of the universe." Well, this is the nature of the universe. We've proven that this is the nature of the universe. We know that this is the nature of the universe. He also suggests that this is not the nature of time. So what happens is that this suggests to us that the true nature of matter is that it does not exist in space. It exists, rather, in time. Now, I would like to say it exists in something else, but I don't have any other dimensions to work with. We have space and we have time. That's pretty much all we have. So it doesn't exist in space. If space doesn't exist, the only thing we have left is time. And so I came up with this time-energy relationship, and I wrote a whole book about it. And it starts on these basic ideas. And I know many scientists refer to it as more philosophy than science, but it is a basic understanding of where physics and science has led us. Now, the fact that scientists, modern scientists, have created the quantum foam is a little bit frightening, as they're still trying to preserve the ether, that material that has infinite density and occupies every cubic picofemtometer of space everywhere, and again, we already know that nothing can be that dense. Nothing has that much density because it would be infinitely dense and therefore infinitely massive. Now, one of the interesting theories that scientists have come up with, and it's been around for quite a number of years, is called string theory. Now, strings, of course, are two-dimensional creatures, and some of them have come up, well, they say up to 26 dimensions, but the most important thing about string dimensions is that they don't have spatial relationships. They have more or less temporal relationships. I'm not an expert on strings. I've looked into the science a bit, but I'm an engineer. So, but I'm also a scientist. And strings, I've kept an eye on these theories, and there was one time there were 5 different theories, and one guy brought them all together and said, this is string theory. Okay, well, this is a way to create a universe with strings. Well, hopefully someday they get past the notion that space is an acting causality, and they get rid of the idea behind that ether still exists, and bring us forward with new realizations, new understandings about the nature of the universe. Well, that covers the basic ideas behind the time-energy theory, which is the shortcut name. This is my book, The Theory of the Time-Energy Relationship. I'm not really trying to sell this book right now. As far as I know, it's not even in print. Well, it best not be in print anywhere, because I'm the publisher and I'm the owner of this book. And there might be a few copies left here and there that you can buy. And I'm not really selling them, but you might be able to buy. No, you can't even buy a version online. But if there's any kind of interest in it, be sure and let me know, and I'll go back to publishing it. At the very least, I'll try and get an online version that you can get on Amazon.com. So, reach me at my website. Once again, I'm Dr. Bob Mertens. Have a great day. Thanks for watching my program.